Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. If you have not already subscribed, please subscribe my channel. Thank you. We continue the discussion of the solutions of the problems that have appeared in the TG set 2024. In this video, we discuss the solutions of two problems at serial number 71 and 72 from the section Algebra. The first question is related to the principle of inclusion and exclusion, and the second question is related to the number of R cycles in Sn, the symmetric group on n letters. These two questions are suitable for all these examinations. Right. We first take up the first question, question number 71 from Algebra, which is related to the principle of inclusion and exclusion. The given question is the number of positive integers less than or equal to 400 which are not divisible by 2, 3 or 5 is. We are given 4 options. Right. And if you see the question carefully, this question you might have done it at +2 level also. Anyway, let's now discuss the solution of the problem in detail. Let capital N is equal to 400 because we have to count the number of positive integers less than or equal to 400 with this property. So n is equal to 400. First, we count how many positive integers less than 400 are there, which is divisible by 2. Let us take it as n2. In general, let nk denotes the set of positive integers less than or equal to 400 which are divisible by k. Now we talk about k is equal to 2. Now the number of elements present in n2 is the floor function of 400 by 2. Floor function is nothing but GIF, greatest integer function. The floor of 400 by 2 is the greatest integer less than or equal to 400 by 2. 400 by 2, that is 200. So, the number of elements present in n3 is floor function of 400 by 3. It is 133. Greatest integer less than or equal to 400 by 3. Number of elements present in n5. Floor function of 400 by 5, that is 80. Now, the number of elements present in n2 intersection n3, that will be given by the floor of 400 by 2 into 3. Because 2 and 3 are relatively prime, it will come as 2 and 3. Agreed? And that will be 66. n2 intersection n5, order of the number of elements is 2 and 5 are relatively prime. Therefore, this is floor function of 400 by 2 into 5, that is 40. And the number of elements present in n3 intersection n5, 3 and 5 are relatively prime. Therefore, it is the floor of 400 by 3 into 5, that is the greatest integer less than or equal to 400 by 3.5, 400 by 15 is 26. Now, the number of elements present in N2 intersection N3 intersection N5. So, number of integers less than or equal to 400 which are divisible by 2 and 3 and 5. Order of number of elements is equal to the floor of 400 by 2 into 3 into 5. They are pairwise relatively prime. Therefore, 2 into 3 into 5, that will come as 13. Right. So, what we have, the number of integers divisible by 2, 3 or 5, 2 or 3 or 5 is number of elements present in N2 union N3 union N5 R. Now, you recall what you have studied at your plus 2 level or even at 10th class also. By the principle of inclusion and exclusion, the number of elements present in N2 plus number of elements present in N3 plus number of elements present in N5 minus the order of N2 intersection N3 minus the order of N2 intersection N5 minus the order of N3 intersection N5. The order means the number of elements present in it plus include number of elements present in N2 intersection N3 intersection N5. Right. Substitute now. Now, order of N2 is 200. This is done by the principle of inclusion and exclusion. Substitute. Order of N2 200, order of N3 133, order of N5 80, order of N2 intersection N3 66 minus 40 minus 26. Last one, order of number of elements present in N2 intersection N3 intersection N5 is 13. Add 413 minus 132. These minus ones are added. Plus 13, that is 294. This is divisible by 2, 3, 5. But what is that we want? We want which are not divisible by 2, 3, 5. How do we get? The total number of elements minus N2 union N3 union N5, the order of. So that is equal to N minus number of elements present in N2 union N3 union N5. That is 400 minus 294. That is equal to 106. Where is 106? Again is option 1. Therefore, the answer to this question is option 1. Right. That is the detailed discussion of the solution of the problem from the section Algebra, question number 71. Let's move to the second question. It is question number 72 from Algebra, and it talks about the number of R cycles. Right. Let Sn be the symmetric group on n symbols. Consider the following statements. Statement 1. The number of 4 cycles in S6 is 180. Statement 2. The number of conjugates of the n cycle 1, 2, 3, n in Sn is n minus 1 factorial. Choose the correct option from the following. We are given 4 options. They talk about only second statement is true, only first statement is true, both first and second are true, both 1 and 2 are false. Right. And we will work out this problem in the next section, next slide. Let's now discuss the solution of the problem in detail. We have Sn, the symmetric group on n symbols. Take the first statement. The number of 4 cycles in S6 is 180. Recall a result from permutation groups. It says in Sn, the symmetric group on n letters, n symbols, there are how many distinct R cycles are there? That was the question. The answer is there are 1 by r into n factorial by n minus r factorial. This is 1 by r into, this is PNR, NPR, number of permutations from out of n taken r at a time. So 1 by r into n factorial by n minus r factorial. So many distinct r cycles are there. But what is that we want? We want 4 cycles. So put r is equal to 4, and in S6, n is equal to 6 in this. So the number of distinct 4 cycles in S6 is the formula. When n is 6, r is 4. And that is equal to 1 by r, 1 by 4 into n factorial, that is 6 factorial, by n minus r factorial, 6 minus 4 factorial. 6 factorial is 720, 1 by 4 into 6 minus 4, that is 2 factorial. This is 720 by 8, that is 90. But it is given in your statement 180. This is not true. Therefore, statement 1 is not true. Let's get into statement 2. The number of conjugates of the n cycle 1, 2, 3, n in Sn is n minus 1 factorial. Agreed. And it is known in Sn any 2 r cycles are conjugate. Any 2 r cycles are conjugate. And we are given an n cycle 1, 2, 3, n in Sn. Therefore, any n cycle is conjugate to this n cycle, that is 1, 2, 3, n. Now, the number of conjugates of the n cycle 1, 2, 3, n is what? Is the number of distinct n cycles in Sn. Right? Right? So, use the above formula only. For r is equal to n. N will be n, r will be n. That will be equal to 1 by r, n factorial by n minus r factorial. For r is equal to n. The number of distinct, in the above example, 4 cycles you have calculated. Now you are calculating n cycles. So, for n only, for r, n, r is equal to n. That is equal to 1 by n into n factorial by n minus n factorial. That is 0 factorial. 0 factorial is 1. 1 by n into n factorial, that is n factorial by n is n minus 1 factorial. Yes, the number of conjugates of the n cycle 1, 2, 3, n is n minus 1 factorial. Therefore, the statement 2 is true. Thus, what is that we have proved? Only the statement 2 is true. Let's look at our options. Here are the options. Option 1 says only 2 is true. Therefore, the answer to this question is option 1. That is the detailed discussion of the solution of the given problem. Right. So, in this problem, you should know this formula. You should know this formula, and the properties of conjugates you should know in Sn. Then this question will be easy. Right. If you are not familiar, go back to this lesson in permutation groups and study about conjugates and conjugacy classes and the number of R cycles. How do we get this formula? If possible, find out a brief proof for all these things. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join in my channel as a member and support me and my channel. Please subscribe my channel if you have not already subscribed. Right. I will be meeting all of you in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.